Welcome to your deep dive. Get ready to shrink down as we explore the world of nanotechnology, specifically molecular machines.
That's right. We're talking about tiny motors even nano cars, all built at a scale that's almost impossible to imagine.
It's like science fiction, except it's real. You sent over some fascinating research, including excerpts from a Nobel lecture by chemist Ben Feringa, the guy who actually won the Nobel Prize for this stuff. What stood out to me was how he drew inspiration from nature.
Absolutely. He talks about how our bodies are full of molecular machines. They're essential for things like muscle movement and DNA replication. But Feringa didn't stop at just observing nature. He aimed to replicate and even surpass it.
And he uses this fantastic phrase, the art of building small. It really captures the essence of this field, doesn't it? It's like sculpting, but instead of clay, they're working with molecules.
Exactly. And just like a sculptor starts with a block of stone, Feringa began with a simple yet powerful concept: chirality.
Okay, now we're getting into the technical stuff. Remind us, what is chirality again?
Think about your hands. They're mirror images,
Mm-hmm.
right? They have the same basic shape, but you can't perfectly superimpose one on top of the other. They're asymmetrical. That's chirality in a nutshell. And it turns out this concept is crucial for building molecular motors.
So how did Feringa actually apply this idea of chirality to create something that moves?
He started by working with these special molecules called overcrowded alkanenes. These molecules have a unique property where they can switch between different chiral forms, kind of like flipping a switch when exposed to light.
So they're like tiny light-activated switches, and he used these to build his motors.
Precisely. Feringa realized that by connecting a series of these light-sensitive molecules, he could create a larger molecule that would actually rotate in a specific direction when exposed to light, just like a motor, but fueled by light instead of electricity.
That's incredible. So he essentially built a motor out of molecules. I read that he didn't just stop there. He kept refining his design, creating multiple generations of these light-driven motors.
You're right. And this constant refinement is a hallmark of nanotechnology. It's all about pushing the boundaries of what's possible at such a small scale. Each generation of his motor got faster, more efficient, and more sophisticated.
It reminds me of those early computers that took up entire rooms. They kept getting smaller and more powerful over time. So we've got these light-powered motors spinning at the nanoscale. Where did Feringa take it from there? What did he do with these tiny motors?
He attached them to surfaces, creating these microscopic landscapes of spinning motors powered by light. You can almost picture these tiny windmill parks whirring away.
Okay, that's a seriously cool visual. But I imagine building a nanocar is a bit more complicated than just attaching some motors to a surface, right?
You're absolutely right. Building the nanocar was a whole other challenge. Imagine a tiny, rigid frame, almost like a chassis. Now, attach 4 of those light-driven motors to it. Those are your wheels. But here's the catch. To make the car go straight, you need all 4 wheels rotating in sync.
Ah, that makes sense. So how did he control that at such a small scale? This is where chirality comes back into play, right?
Exactly. Think of it like this. Imagine your left and right hands are now the front tires of our nanocar. They both need to turn the same way for the car to move forward. But if one hand is flipped like a mirror image, they'll steer in opposite directions and you'll go nowhere.
So by carefully selecting the chirality of each molecular motor, essentially deciding which way each hand is facing, Feringa could control the direction of the nanocar.
Precisely. It's mind-blowing when you think about it. He's essentially steering a car by controlling the twist of individual molecules.
This is incredible, but hold on, we've only talked about light power in these motors. Didn't Feringa also explore other energy sources?
You're right. While light is fascinating, he also investigated using chemistry itself as fuel. Imagine a motor powered not by electricity or light, but by a series of chemical reactions, much like how our bodies use ATP for energy.
So instead of plugging it in, you'd feed it chemicals. What's even more amazing is that he actually managed to create these chemically powered motors, right?
Yes, he even built tiny particles that, get this well invented, can propel themselves through water by catalyzing the breakdown of hydrogen peroxide.
Wait, so they're like tiny self-propelled submarines swimming around.
Exactly. It's like taking a page right out of nature's playbook, mimicking how single-celled organisms move around. So we've got light-powered motors, chemically powered motors, even motors that catalyze reactions to move down. Where does it go from here? I mean, what's the practical application of all this? It sounds amazing, but can we actually use these molecular machines?
That's the million-dollar question, isn't it? We've talked about these incredible motors, this mind-blowing nanocar, but how does it translate into something that could actually impact our lives?
That's what makes this feel so exciting. The potential applications are vast, Remember those liquid crystals Feringa was manipulating with his motors? Imagine applying that to electronics.
Okay, yeah.
We could see faster, more efficient displays for our phones and computers.
So like our phones could refresh instantly without draining the battery. That'd be amazing.
Exactly. But it goes beyond just screens. Think about sensors.
Hmm.
Imagine these tiny machines detecting specific molecules with incredible sensitivity.
You're talking about medical diagnostics, right? Instead of drawing vials of blood, we could have these nanobots swimming around sniffing out any problems.
You got it. Early disease detection, real-time monitoring it, could revolutionize healthcare. And that's not even scratching the surface of what's possible. Think about self-healing materials.
Wait, like a scratch on your car just disappears overnight? Sign me up. But seriously, how does that even work?
It all comes down to programming these molecular machines to repair damage at the molecular level. Imagine a small tear in a fabric. Tiny motors could be triggered to weave the torn edges back together.
That's mind-blowing. So from what I'm hearing, we could be on the verge of a future with super efficient electronics, personalized medicine, and self-healing materials, all thanks to these tiny machines.
It's a future brimming with possibility, but it's also important to acknowledge the challenges. We're talking about manipulating matter at the atomic and molecular level. It's incredibly complex. One of the biggest hurdles is figuring out how to control these machines once they're inside a living organism.
Right, we don't want a rogue nanobot situation on our hands. It's
Yeah.
not like they come pre-programmed with Asimov's laws of robotics or anything. So what are scientists doing to address that?
Biocompatibility is a major area of research. These machines need to operate safely within the body without triggering an immune response.
So they need to be stealthy little nanobots. And then there's the whole issue of targeted delivery, right? We need to make sure they end up exactly where they're needed.
Absolutely. Precision is key. But it's not just the biological challenges, there are also technical hurdles. Synthesizing these molecular machines is a complex and time-consuming process. Scaling up production to meet potential demand is something researchers are actively working on.
It's like anything else. We need to figure out how to mass produce these things if they're going to have a widespread impact. It sounds like we're still in the early stages, but the potential is mind-boggling.
It truly is, and I think that's what Fringa meant by the art of building small.
Mm-hmm.
It's not just about the incredible technical achievements, it's about pushing the boundaries of what's possible and imagining a future that seems like science fiction today.
And who knows what the next generation of scientists will dream up. Maybe they'll look back at Feringa's work like we look at the Wright brothers' first flight, a pivotal moment that sparked an entirely new era. If there's one thing I'm taking away from this deep dive, it's that the future of nanotechnology is brimming with potential.
I completely agree. And just like Feringa found inspiration in the intricate machinery of life itself, I'm excited to see how this field continues to blur the line between nature's designs and human ingenuity.
Well, on that note, we've reached the end of our deep dive into the world of molecular machines. It's been an incredible journey, exploring everything from the art of building small to the vast potential these tiny machines hold.
It's been a pleasure joining you on this exploration.
And a huge thank you to you, our listener, for taking this deep dive with us. We hope you've enjoyed this fascinating glimpse into the future of nanotechnology. Until next time, keep exploring.